Okay, so here's the second part of the video about polynomials. I need to start by making a correction. I made a silly mistake at the end of the last video. You'll notice here that if I can just here the constant d was in fact not was not 17. Let me just get this right. D was in fact 19. Whoops, wrong colour there. Let me just change the colour. Just bear with me a moment. So D was 19 and E was actually 133 because there was a 5 there. 5 equal to that, so E was 133, and so the correct remainder was 19x plus 133. So I hope that didn't cause any confusion. Now let's go back and review where we're up to. We have we've defined polynomials, we've understood the term identity, we've defined polynomials, we've considered polynomial arithmetic, we've learned the method of equating coefficients, that's very important, and now we're going to go on to consider factors and remainders. And I think to start this session, let's go back here and see that we learned how to divide a polynomial by considering the degree of the quotient, the degree of the remainder, and then equating coefficients. So this section here is all about equating coefficients. Okay, let's look at another example, actually a slightly simpler example. Let's look at a polynomial as such as, let's see, p of x equals 3x to the power 3, or 3x cubed minus 5x squared. Plus 7x. Now let me get this right. Minus 5. So obviously the degree of this polynomial is 3. This is what we call a cubic. This will be the most important type of polynomial for this section. And let's consider what would happen if we try to divide the polynomial p by x minus 1. So here we have a polynomial degree 1, a linear function, x minus 1. Now, how would I go about doing that? I would use the same method as above. I would use the equating coefficients method, and it would look like this. Px over x minus 1 must be equal to some quotient function, quotient polynomial qx, plus some remainder polynomial divided by x minus 1. And as before, we're going to multiply this. Oops, excuse me. We're going to multiply this out and write p of x. Oh, and by the way, this is again an identity. Is identically equal to q of x, the quotient, times x minus 1 plus r of x. Now let's apply our method as before. Remember here px is this cubic polynomial here. So the degree of the left-hand side is, again, 3. The degree of the right-hand side must be 3. Now what's the rule about the degree of the remainder? Do you remember the rule? The degree of the remainder must be less than the degree of the divisor. What's the divisor? The divisor is this function here. What's the degree of the divisor? The degree of x minus 1. Degree of r is less than the degree of x minus 1. That's 1. So the degree of r is 0. What does it mean if the degree of r is 0? Well, that means that r is a constant, just a number. In fact, we're going to write not a, but we're going to write r is equal to capital R. So here the capital letter R just means a single number. So I'm going to be able to write P of x is equal to Q of x times x minus 1 plus a number R. Now, as before, we can use the method of equating coefficients here. Let's first of all copy out. Let's copy out the. What is going on here? Sorry, I'm just having a slight confusion here as to where my tools are. Just bear with me a moment. Tools. Yeah. Not quite sure why I don't have. Hang on, let me just pause the video for a moment. Okay, back in business. Excuse me for the delay. What I'm going to do now is just copy out this this polynomial again, and this will form the left-hand side of my identity. So I'll move this object down here. Here we go. And by the way, I've forgotten, as people often do, to write the third bar there because that's an identity. So the right-hand side is now of the form qx times x minus 1 plus a number r. Now let's ask ourselves, what's the degree of q? Do you remember how to work this out? The degree of q, what should that be? Well, the degree of the left-hand side is 3, so the degree of the right-hand side must be 3. The degree of this polynomial is 1, so this polynomial must have degree 2. So we can now write a general form: 3x cubed minus 5x squared plus 7x minus 5 is identically equal to ax squared plus bx plus c times x minus 1 plus a single number r. And now we're going to equate coefficients. Equate coefficients. So we're looking at the coefficients on the left-hand side and the coefficients on the right-hand side. And just to be different, I'm going to start in a different order. I'm going to start by considering the coefficients of x to the 0, or the constant terms. On the left-hand side, what's my constant term? It's clearly minus 5. On the right-hand side, what's my constant term? Well, it's not just r, it's also minus c. So it's minus c plus r. So minus 5 is equal to minus c plus r. Now, when I examine x to the power 1, I get left-hand side coefficient is 7. And on the right-hand side, and I'll just skip writing this, on the right-hand side, the coefficient of x, we can work out, we get c times x, but we also get minus b times x. So c minus b times x. X to the power 2, I get the following equation, minus 5 on the left, and on the right, x squared, I need minus a plus b. And finally, the coefficients of x to the power 3, I get 3 on the left-hand side equal to a on the right-hand side. So this equation here is already giving me the value of a, from which I can get b, c, and r. So a is 3, b, now let's be careful, if a is 3, then b is minus 2. Hold on, sorry. A is 3, so yeah, b is minus 2, c is equal to 7 plus b, so c is 5, and finally r, so c is 5, so r is 0. Okay. Now let's consider what this means here, this last line. Remainder is 0. Remainder equals 0. What does it mean if the remainder of a division is 0? Well, it means we found a factor. Yeah? So we have found a factor. So we can write a complete multiplication like this. This polynomial is identically equal to qx, which we worked out as 3x squared, because a was 3 minus 2x plus 5, 3x squared minus 2x plus 5 multiplied by the divisor x minus 1 plus a 0 remainder. So we obviously don't have to write that. This means that x minus 1 is a factor. X minus 1 is a factor of the original polynomial 3x cubed minus 5x squared plus 7x minus 5. So let's key into that idea. Factor. Factor means the remainder is 0. Now we're going to look at examples of this type in a more general way. And when I say examples of this type, I mean examples with divisors which are linear. So this function here is linear, so it's a linear divisor, and in this case is in fact a factor. And we're going to examine what's called the factor theorem. So for this I'll just switch over to my PowerPoint and we'll look at this idea in a bit more of a general way. Okay, I'm having a bit of a problem here. Maybe that was just a aha, okay, good, we're ready. So the remainder and factor theorems. So if we look at the general case here, in this case a is the starting polynomial, the dividend, b is the divisor, so a over b is q plus r over b. So b is the divisor, q is the quotient, and r is the, tell me, the remainder. That's right. So now we're considering what happens if b, the divisor, is a linear function. Well, that means we can write b as x minus some number, alpha. Now it's true we could have something like 2x minus alpha or 3x minus alpha, but that doesn't really change the basic pattern. So we'll just assume that b is like this, x minus some number alpha. Okay. What do we know about rx? What can we say about rx? So if you were paying attention a moment ago, you'll know we can say it's a constant. So we can write ax is always x minus alpha times qx plus r. Now notice, very important, this is an identity. So this is true for every value of x. Doesn't matter what x is, this is always true. So what's the consequence of that? Can you see, is there some particular value of x I can choose? You might think, for example, it's worth choosing x equals 0. Or if we put x equals 0, we get a0 equals minus alpha times q0 plus r. That doesn't really help us very much. But there is a special value of x we can choose. We can set x equals alpha. Then we get a alpha equals 0 plus r. Let me just show you that again. Whoops, I think I've gone the wrong way. Sorry. Not quite used to using this technology here. So let me just go forward a few points. Okay, that was the answer to the previous problem. Here we are. So what I was about to say was, in this identity, if we set x equals 0, the magic of it is that if we set x equals alpha, then this quantity here is 0, which means that this whole part disappears. So a of alpha, remember a is a polynomial. If we put alpha into the polynomial, we get r. So if we put alpha into the polynomial, we get r. And by the way, this is an equation, actually, not an identity. That's a mistake. So what does that actually prove? It proves that if x minus alpha is a factor of ax, then a alpha is 0, because if something is a factor, it means specifically that the remainder is 0. You can say x minus alpha divides ax exactly. So here's another question for you. If x minus 3, for example, divides some polynomial px exactly, what does that tell you about the graph of px? Well, if x minus 3 is a factor, it means that 3 is a root of the equation px equals 0, or equivalently that the graph cuts the x-axis at 3. Okay, so I'm going to escape out of this now. I'm now going to go back to the main area here. So let's consider the factor theorem and the remainder theorem together, because they're really one particular theorem with two forms. So let's give this a heading. Factor theorem and remainder theorem. So these are stated the other way round to what we just learned. If p alpha equals 0, it follows that x minus alpha is a factor of px. So you have to imagine px is any old polynomial. If we put a number, alpha, could be 2, could be 7, could be minus 6, into px, and we get 0, it follows that x minus that number is a factor of px. And we can also say if p alpha equals k, it follows that x minus alpha, let's write this slightly different, px divided by x minus alpha px leaves remainder k when divided by x minus alpha. So you might be getting a little bit confused now, so I want to give you some very specific examples to show you how this works. Let's first go back to our polynomial here that we had before. Just type it out again here. So this is our example. Suppose this is px. Now p of 1, if we put the number 1, we get 3 times 1 minus 5 times 1 plus 7 times 1 minus 5 equals 0. And the factor theorem tells us that this implies that x minus 1 minus the number we substituted is a factor. So we can do this and immediately see that x minus 1 is a factor without actually doing any division as we did up here. So not that that was wrong, but it's a quick way, a shortcut, which we can use in some situations. Now suppose instead of using 1, I put the number 2. What would I get? P of 2 is 3 times 8 minus 5 times 4 plus 7 times 2 minus 5. Well, what does that come to? 24 minus 20, so that's 4, plus 14, that's 18, minus 5, that's 13. Now, my question to you is, what does this number tell us? What information have we got by doing this calculation? Can we apply the factor theorem? Well, no, because the factor theorem only applies if p evaluated at that number gives 0. Here it's not giving 0, it's giving 13. So we have to apply instead the remainder theorem. Yeah? Let me just annotate here. This is the remainder theorem, and this is the factor theorem. So the remainder theorem here is telling us that the remainder, when p of x is divided by x minus 2, it gives us a remainder of 13. We have remainder 13. So very often in the exam you'll be given information, let's say like this, that the remainder is 13, and you work backwards and you deduce something about the original polynomial p. So that's how it usually works. Okay, let me save my file here. So those are the factor remainder theorem, and I strongly recommend that you read the statements of the theorems in the book and double check that you understand it. Okay, so again, if you properly understand this process, which requires that you understand what is an identity, requires that you understand how to equate coefficients, then it should be easy to understand what these two theorems are really saying. Now, why are they useful? They're useful precisely because you can find the remainder, or in some cases find a factor, very quickly. They're just quicker ways of doing things that otherwise would take time. Okay, so we now hopefully have some idea what the factor and remainder theorems are. Let's consider for a moment what's called the extended form. Extended form of the factor theorem and the remainder theorem. Well, this is very simple. This is just the case where we divide p of x by something not as simple as x minus 1, perhaps 3x minus 2. So here I'm going to take a different example for p to keep it nice and simple. I'm going to use the example p of x is x squared minus x minus 1. And suppose we want to divide this by this. Okay? So again, we're going to use a shortcut. Use the remainder theorem. The remainder theorem tells me, in extended form, is telling me that by the same logic as above, I can simply write p of 2 over 3. Now, why p of 2 over 3? Because if I put x equals 2 over 3 in here, I get 0. And we already know that the remainder is exactly what we get. Let me show you again in the PowerPoint. The remainder is exactly what we get if we set x equal to the value that makes this linear factor constant, or this linear divisor constant. So if I set x equal to 2 over 3, I'm going to get 2 over 3 squared minus 2 over 3 minus 1. So what's that? That's 4 over 9 minus 6 over 9 minus 9 over 9. So it's minus 15 plus 4, or minus 11 over 9. This is the remainder. This is the remainder if we divide this polynomial by this linear factor. So you see the extended form is only changing in the sense that we're allowed to put a number here in front of the x, but then we simply again choose the value of x which makes this whole thing 0. So let's look at another example. Suppose we wanted to know the remainder. So example, find remainder when 2x to the power of 4 minus 5x plus 7 is divided by 3x plus 1. So do you see how you can use the extended form of the remainder theorem to answer this question? So what you need to do is to evaluate, so let's say answer, evaluate polynomial when x is equal to which value? It needs to be the value that makes this divisor 0, so it's minus 1 over 3. So it's a bit of a horrible number. Remainder is equal to 2 times minus 1 over 3 to the 4 minus 5 times minus 1 over 3 plus 7, which is equal to something. What is that? Minus 2 over 81 plus 5 over 3 plus 7 equals, use your calculator and find the answer. So I want you to note something very important. What I just did is much easier than long division, yeah? Not just much easier, but much quicker. Yeah? So this gives you the remainder through a simple bit of arithmetic that you can do on your calculator just in a few seconds. Now, suppose I take the whole problem and change it slightly. So I'll take that problem and copy it, but I'm just going to slightly change it. And I'm going to change the divisor. So instead of 3x plus 1, we're going to use x squared minus 4. Oops, sorry, I've chosen the wrong... there we go. X squared minus 4. So now my divisor is x squared minus 4. So here's what you might do. You might say answer. Use remainder theorem. Set x equals 2, and the logic is, well, if x equals 2, then the divisor is 0, so we should get the correct remainder. And what do we get? We get 2 times 2 to the power 4 minus 5 times 2 plus 7, which is 32 minus 10 plus 7, which is 29. So is that the right answer? Is this the right answer? Is 29 the correct answer to the problem? The problem was find the remainder when this polynomial is divided by this divisor. No, it's wrong. It's definitely wrong. How do I know it's wrong without checking the numbers? Well, because when 2x to the 4 is 2x to the 4 minus 5x plus 7 is divided by x squared minus 4, we're going to get a quotient, and we're going to get a remainder divided by x squared minus 4. But what is the degree of the remainder? The degree of the remainder, is it 0? Is the remainder a constant? No, the remainder is not necessarily and usually will not be a constant, because the degree of the divisor is 2, so the degree of the divisor the degree of the remainder is less than 2, is 1. So r of x is a linear function like this, ax plus b. So look, this answer here is just a number. So what we need here is a big warning. Only apply remainder theorem or extended form of the remainder theorem or factor theorem, they're all basically the same thing, with linear divisors, so ax plus b divisors. So that's a big mistake that people sometimes make, so watch out, don't do that. only apply the theorem with linear divisors. Here this divisor is not linear, x squared minus 4, not linear. This divisor, 3x plus 1, is linear, so we can put a tick here. This is the right kind of divisor, so we can use the remainder theorem. Okay, so those are the factor and remainder theorem. You need a lot of practice with those theorems, how to use them to quickly get answers. There are tons and tons of examples in the additional maths book as well as the P2 book that will let you practice using them to calculate different numbers, different answers. Now, how can we use these ideas that we've just seen, these very powerful but simple ideas of factor and remainder theorem? Here they are. How can we use them to help us solve cubics? So let's just put a tick. We've done factor and remainder theorem, although very briefly. You need a lot of practice. How can we use them to solve cubic equations? So let's go back to let's write some examples. I'll write a different example just for variety. So let's make a little title now, solving cubic equations, and here's an example. Okay, let me try and come up with a good example. X squared, that's a bad start, isn't it? It should be cubic, not quadratic. X cubed minus 8x squared plus 10x, and then maybe minus 3. So suppose this is a cubic equation. We want to find the roots. So solve is the same thing as find roots. So there may be only one root, there may be two in a special case, and there may be 3 roots. It's actually impossible for there to be 0 roots, but more about that in a moment. So before we actually try and solve this this problem, let's look at a different cubic equation. X minus 1, x minus 2, x minus 3 equals 0. I hope you can see this is cubic, but it's already solved because it's factorized. So because it's factorized, we can clearly see there are three roots, x equals 1, 2, and 3. Okay, so that's not very interesting, but my point is that we need to go from this form to this form. We need to factorize the equation in order to find the answers, just in the same way as you factorize quadratic equations to find the solutions to those equations. Now, the question is, how do we do it? So I think what I'll do is I'll just remove this whole section because it's not actually helpful to us right now. And we're going to think about how to factorize this. So first question you'll have is you'll probably think, well, I know that this is the answer if we're dealing with a quadratic equation. Excuse my formatting there. But is there a similar equation I can use for cubic equations? The answer is yes, but it's interesting. There is a general formula, but it is very, very difficult to use. It's very complicated. So we don't actually teach that formula at this level, and in fact most of the time you won't use the general formula even if you're going on to university maths, because it just isn't very useful. Of course it can be done on computers, but so I want to say first that in some cases it can be very difficult to find the answer. Or let's say difficult or complicated to find the answer. In other cases we can guess. So it might seem funny that I'm going to teach you about a guessing process, but that's what I'm going to do. I'm going to teach you how to guess answers and then find out if those answers are right. So how do we guess answers? What we do is we search for a linear factor, because a linear factor will correspond to a single root. So what we're looking for is some structure like this: x cubed minus 8x squared plus 10x minus 3 is identically equal to, because remember we're just factorizing, rewriting the same thing, x minus alpha times q of x, where q is the quotient and 0 is the remainder because it's a factor. So if 0 is the remainder and this is a linear divisor, then we can apply the factor theorem. The factor theorem tells us that if this structure is possible, then p of alpha is equal to 0, where p of x is the name of the original polynomial. Yeah? So that's what the factor theorem says. So what we're looking for is a particular number, alpha, which makes this 0 when we substitute it. Then that must be a linear factor. Now, once we've done that, the remaining part of the problem is easy, because what's the degree of q? Well, the degree of this is 1, so the degree of q must be 2. So if the degree of q is 2, then it's of the form ax squared plus bx plus c. And we know how to factorize this function because it's a quadratic function, so we can change this into ax minus beta x minus gamma, something like that. So we can factorize that easily because it's quadratic. So it's only this first step that's difficult. The first step is finding a linear factor. So how do we find a linear factor? By guessing. That's the next question. So before I solve it for this problem, I want to show you the general idea. Suppose in general that we have p x is equal to ax to the power 3 plus bx to the power 2 plus cx plus d, and suppose we want to transform this into a product of two factors, sx minus t times, I'm going to find some good letters here, let's see, ex squared plus fx plus g. That's the structure we're looking for. The question becomes, what is the relationship between these two key numbers s and t, which we're going to need in order to find our linear factor, and these numbers a and d? What is the relationship between them? And this is not very obvious, so I certainly wouldn't expect anyone to kind of figure this out on their own in an exam. It's something you should just know in advance. So let's write, remember, because this is an identity, we can make some observations about these numbers. First of all, let's observe that a, b, c, d, s, t, e, f, g can all be integers. Okay, we're not going to deal with irrational numbers. That's more advanced than our course would be involved in. And if they're fractions, we can multiply the whole equation by the denominator and just change them all to integers. So let's assume they're all integers. Then we have the following integer equations by comparing coefficients, or rather equating coefficients. Equating coefficients gives us the following information. Let's keep that in the screen there. So a is equal, looking at the coefficient of x cubed, a is equal to s times e. And d, comparing the constant term, the d here, the constant term must be equal to minus tg. So what does that tell us about the relationship between a and d and s and t? Well, it means that s is a try and write in English there. S is a factor of A, and T is a factor of D. Okay, so what is that telling us exactly? It's telling us that if we go back to our original equation here, A was 1. So if S, again looking here, if S is a factor of A, S must be 1, because the number 1 the number 1 has only the factor 1, although it can be negative. It can be negative 1. Similarly, if we look at this constant term minus 3, D is minus 3 here, well, that means that T has to be a factor of 3 or minus 3. Okay, so we're going to see this gives us a list of possible values that we can choose for our linear divisor. And for each of those examples, we can check if the factor theorem applies or not. Okay, so I'm going to write again, I'm going to copy this out again, this example, like that, and I'm going to show you how you can use this idea to easily get the answer. So we have this structure so far. What's the next step? Try values of alpha which are factors of the integer minus 3. Well, the only factors of the integer minus 3 are plus or minus 1 and plus or minus 3. So this gives us the following possible factors: x minus 3, x, oops, what am I doing there? X minus 3 or x plus 3, and x minus 1 and x plus 1. You see, I basically have 4 possibilities. Positive and negative are both allowed, but the only integers that could work are 3 and 1. Plus minus 3, plus minus 1. So I only have 4 possibilities to check. Let's start with the easiest. Start with the easiest example. X minus 1. If x minus 1 was a factor, then the factor theorem would tell us that by substituting 1 in here we should get 0. P of 1, let's check. We just have to check, you see. 1 cubed minus 8 times 1 squared plus 10 times 1 minus 3, which is equal to 0. So, true. So for this case it's true. Now if that weren't true, if that number came out to be a number different to 0, we should simply continue along this list. Yeah? Just keep trying all of these examples until one of them works. Now you can use your calculator, of course. You don't have to write out all the details of these calculations, but you do need to make it clear in your exam questions and your working. Show the working out, show that you've tried, show that you understand which numbers are possible, and show that you've actually tried to make some evaluation or calculation of the polynomial at those values until you found one linear factor. So let me emphasize now, when you find one linear factor, stop. Why do we need to stop? Well, we don't need to stop. We could keep trying the other linear factors as well, but instead the most logical thing to do is then to consider q of x and factorize it as a quadratic, because you already know how to do that. So let's see how that works in this example. If p of x is now known to be equal, let me just change this to x minus 1 times q of x. Well, we'll just write q of x in its general form, ax squared plus bx plus c. because we know it's quadratic, so we know it has degree 2, so it must be of this form. And we just have to find a, b and c, and then factorize, and we've finished. So first, if we consider coefficients of x cubed, we can clearly see that 1 on the left hand side must be equal to 1 times a on the right hand side, so that a is equal to 1. If we consider coefficients of x squared, we see that minus 8 on the left hand side must be equal to a. Minus 8 on the left hand side must be equal to minus a, but be careful, there's another x squared plus b, so that b is equal to minus 8 plus a minus 7. And if we now consider coefficients of x to the 0, for example, we see that minus 3 on the left must be equal to minus c on the right, so c is equal to 3. So we now have a partial factorization of the function x cubed minus 8x squared plus 10x minus 3 is identically equal to x minus 1 times x squared minus 7x plus 3. Now let's just double check that makes sense. Yeah, minus 8x squared, yeah, okay. And now you can simply use the methods you already learned at school how to factorize this. Okay, so it's not going to work, is it? 49 minus 12 giving 37. So just quickly working out those two roots, they are 7 plus or minus the square root of 49 minus 12 all over 2. So we have something like x minus 1, let's see, x minus 7 over 2 minus root 37 over 2, x minus 7 over 2 plus root 37 over 2. So this is the final answer. This is the complete factorization of this original cubic, which means the three possible values of x are x equals 1, or x equals 7 over 2 plus root 37 over 2, or x equals 7 over 2 minus root 37 over 2. So these are the three answers. Now let me remind you that, as I said earlier on, that you won't always get three answers, because if you think about it, this quadratic here may not have any roots. It may have 0 roots, in which case there would only be one answer. Or it may have a repeated root. It may have the same root repeated twice, so we may get 2 answers. Or, as in this case, we may get 3 answers because the quadratic has a delta greater than 0. Okay, so that is how, it's a little bit complicated when you first see it, but that is how you can solve some, and I emphasize some. In some cases we can use this guessing method to find linear factors. So I'm going to pause the video now, and I'm going to find a second example that we can try, and then we'll stop there. Okay, so here's another example I found on one of my homework sheets. So how do we solve this one? Do you remember the steps? It's a bit complicated when you first think about it, but here we go. So first of all, we're going to observe that the constant term is 6. Oh, by the way, I should have said, please go ahead and try it on your own first. Pause the video and then see if you agree with my method. So the constant term is 6. The coefficient of x cubed is 1. So any linear factor, according to what we discussed, is of form S x minus t, where s divides 1 and t divides 6, remembering that they are allowed to be negative. Okay, so possibilities, possible factors are x minus 1, x plus 1, x minus 2, x plus 2, x minus 3, x plus 3, x minus 6, x plus 6. Now notice here we can't have something like 3x minus 1 because 3 is a number which does not divide 1. Notice also we could have minus x minus 1, but that's pointless because minus x minus 1 is just minus times x plus 1, so it comes to the same thing. So really these are the only 8 genuinely different possibilities. As we said before, it's always logical to start with the simplest and then go on to the more difficult ones as we go along. So keeping the question in mind there, let's try them out one by one. So let's try x equal to 1. So here I'm using the factor theorem. If x equals 1 and the polynomial is 0, then x minus 1 is a factor. So I'll substitute 1 in here. I get 1 minus 4 plus 1 plus 6. This is not 0, so that's no good. So I'll try x equals minus 1. I get minus 1, minus 4, minus 1 plus 6, and that is equal to 0. So what do we do now? We stop. We must stop because we want to examine the quadratic factor separately. So we can write now x cubed minus 4x squared plus x plus 6 is identically equal to x plus 1 times some quadratic ax squared plus bx plus c. And now we're going to examine, we're going to equate the coefficients. Now when you get used to this, you're going to find it very easy because first of all, let me show you some tricks. Notice that the 6 as the constant term is equal to the 1 times the c, so you immediately know that c must be 6. Notice also that the coefficient of x cubed is 1, and the only x cubed here is ax squared times x, so a is obviously 1. So the only one that's a bit difficult to find is b, and the easy way to find b is to notice that 1 here, the coefficient of x, must be equal to c plus b. Well, c is 6, so b is minus 5. So I've immediately got those three numbers, which allows me now to write out the quadratic factor clearly. I have x cubed minus 4x squared plus x plus 6 is identically equal to x plus 1 times x squared minus 5x plus 6. And this is very easy to factorize. It's x plus 1, x minus 2, x minus 3. So we see that the answer is x equals 2, 3, or minus 1. So that's another fairly easy example of how to solve these cubics using this guessing method, but be aware they can get a bit more difficult. But you should also be aware that this is exactly what is needed on the exam. I'm showing you here the exam syllabus, and you'll notice here factors of polynomials. You need to know and use the remainder and factor theorems. You need to find factors of polynomials, and you need to solve cubic equations. But let me be really clear, it is only those quite easy cubic equations that you need to solve. There are many much more difficult cubic equations to solve. For example, x cubed minus x minus 1 equals 0. It's difficult to solve. You notice that if we put 1 in here, we don't get 0. If we put minus 1 in here, we don't get 0. And in fact, we can't use our trick here because only 1 and minus 1 are suggested. So notice for this example the above method doesn't work. And the reason it doesn't work is because the answer is not a rational number. So because the answer is not a rational number, so it's not that it doesn't exist, there is an answer, but it's not rational. And because it's not rational, this argument that I showed you way up here of considering the factors of the numbers, that only worked because we were dealing with integers. So if the factors here are not rational, that won't work. So we won't be able to use the method. And just to satisfy your curiosity, for those of you who want to know what the general formula is, I'll show you this document, which is something I put together a couple of years ago. At least it should be. Okay. Something I put together a couple of years ago, which is a little bit of information about how to solve cubic equations using a formula. Let me just scroll through it and you'll see that there's quite a complicated process to go through, and that the final answer, even in very simple cases, this simple cubic here has an extremely complicated answer which works out to about 1.552169. But you can see this is crazily difficult, and of course this is not on the exam, so let me be really clear, that is not necessary for the exam. So let me just go back to the beginning of the document, and hopefully you can see that we've now covered all the areas. So well done if you got this far. That was the last area we needed to cover. So all you need to do now is go to the book and practice, and if you do that, you should be fine. Okay, thank you very much.